Welcome to our deep dive. Today, we're jumping right into the beating heart of modern 2026 manufacturing. Whether you're a total beginner to machining or a seasoned engineer looking to optimize your supply chain, you are going to want to stick around for this. We're ripping the lid off CNC turning. We'll see exactly how those ultra-high precision cylindrical parts, everything from aerospace fasteners to automotive drive shafts, actually get made. Ready? Let's get right into it.
So here's our game plan for today. First, we'll cover the core concepts, specifically turning versus milling. Then, a step-by-step breakdown of the machining process. Third, we'll look at the hardware, spindles, and live tooling. Fourth, we'll compare metals against engineering plastics. And finally, we'll wrap up with strategies to lower your costs and part complexity.
All right, part one, concept, turning versus milling. It's all about understanding the logic of subtractive manufacturing.
People mix up turning and milling all the time. But it's actually pretty simple if you think about it like this. Picture a potter's wheel. You've got a lump of clay spinning really fast, right? And the potter's hands, which act like the cutting tool, stay relatively still to shape it. Well, that is turning in a nutshell. It's absolutely perfect for making symmetrical, round parts. Milling, on the other hand, that's more like taking a handheld power drill to a piece of wood clamped to your workbench. The tool spins, but the material doesn't move at all. So in this world of subtractive manufacturing, the whole logic of turning is just peeling away a solid bar of material into your final shape with as few cuts as possible.
Moving on to part two, our step-by-step machining tutorial. This is the journey from a digital concept to a physical part. Now, this whole process actually starts way before the machine even turns on. Step one, an engineer builds a precise 3D model in CAD software. Step two, that model gets translated into CAM software, which spits out G-code, basically the language the machine actually understands. Next up is step three, which is crucial, digital twin simulation. We'll talk more about that in a sec. And finally, step four, the actual physical cutting. We start with roughing to quickly hog out the big chunks of waste, kind of like peeling an onion, and then follow up with finishing passes, which uses super light contact to guarantee strict dimensional requirements and a perfect surface finish. Honestly, in 2026, digital twin technology is practically a superpower. Before a single millimeter of metal is ever cut, simulating the process in this virtual environment prevents disasters. It warns you about disastrous collisions between your cutting tools and the chuck. It plans out the absolute fastest toolpaths. And get this, it even predicts exactly when your tool will wear out based on the material. It's literally like having a real-time undo button before a crash even happens. It adds so much certainty to commercial production.
Let's hit part three. Hardware, spindles, and live tooling. We're looking at the anatomy of a turning center. Okay, so the heart of any lathe is its spindle and the work-holding system. The spindle provides all that massive torque and speed, while the fixtures hold on for dear life. The three-jaw chuck? That's your everyday workhorse for gripping large, round, or hex stock. But for tiny parts spinning at insanely high RPMs where you need perfect concentricity, you're definitely going to want to use collets. And for heavy-duty, high-volume production, hydraulic actuators act like these massive, powerful robotic gloves. They stop the part from deforming and keep everything perfectly safe while spinning at crazy speeds. But here is the real game changer: live tooling. If traditional turning is just stripping material away, live tooling totally flips the script. It's basically like cramming a miniature milling machine right inside the lathe. When the main spindle stops and locks into a precise angle, that's called C-axis control. These little powered tools housed in the turret can drill, tap threads, or mill features straight into the side of the part. That means you don't have to move the part to a whole different machine for secondary operations. It's a massive win for commercial efficiency, drastically cutting down labor costs and handling errors. And this brilliantly illustrates how specific cutting geometries map to real-world applications. Facing, for example, creates a perfectly flat surface at the end of the part to establish a precise datum surface. Those ultra-precise cones in high-pressure nozzles? That's taper turning. If you're making fasteners or fluid connectors, you're relying on threading. And those little channels for O-rings to stop oil leaks? That's grooving. Literally every single one of these operations builds the industrial components we use every single day.
All right, part four, metal versus engineering plastics. Let's see how your material choice actually drives commercial outcomes and cycle times.
Metals absolutely dominate the industry because they are incredibly predictable and stable. They can handle blisteringly high spindle speeds, making them perfect for cranking out tens of thousands of parts in high-volume runs. But now, in 2026, advanced engineering plastics like PEEK or PTFE are getting super popular because they're insulators and chemically resistant. But let me tell you, machining plastics is tricky. They absorb moisture from the air, they expand the second they get hot from cutting, and they create these flexible, gummy burrs that smear and are a total nightmare to remove. It is a serious challenge in dimensional management for any machinist.
Even within metals, the commercial realities are vastly different. Aluminum is kind of the fast food of machining. It cuts like butter, you can run it at super high speeds, and the cost per part is incredibly low. But switch to 316 stainless steel. Sure, it's super corrosion resistant, but you have to drastically slow down your speeds or you'll burn right through your tools. And the toughest of all is grade 5 titanium. It holds on to heat like crazy. The heat literally gets trapped right on the cutting edge, forcing you to buy really expensive carbide tooling and blast it with high-pressure coolant. Basically, the material you pick directly dictates your tooling requirements and how big your bill is going to be.
Which brings us to our final section, Part 5, Strategy. Lowering cost and complexity through design for manufacturability, or DFM. Let's see how procurement managers and engineers extract maximum value.
So, think about this. How can one tiny, simple design change result in 20 to 40% cost savings? Seriously, it's not magic. It's the massive financial impact of smart engineering.
There are a few golden rules of thumb you absolutely have to follow. First off, minimize sharp internal corners. The boring bar on the machine has a radius. If you match your design's corner radius to the tool, the machine can just swoop right through in one smooth motion. Second, reduce part complexity. If a feature isn't strictly functional, like a purely cosmetic chamfer, just ditch it. And the biggest one, standardizing tolerances. Engineers love to slap super strict plus or minus 0.005 millimeter tolerances on everything. Don't do it. Overspecifying just shoots your scrap rates through the roof and needlessly increases inspection times.
In high-volume production, balancing quality with speed is everything. Just imagine shaving a mere 5 seconds off the cycle time for a single part. Over hundreds of thousands of parts a year, you are saving thousands of dollars. To get that kind of extreme efficiency, you utilize high-feed tools and automate with bar feeders. Automation is the key here. That lets the machines run unattended all night long in a lights-out, continuous manufacturing setup. And whenever possible, spec out free machining materials to keep things running super fast.
The technology just keeps evolving. The most fascinating 2026 advancement in turning is autonomy. Our modern AI-integrated controllers literally have ears now. They can hear the vibration frequency of tool chatter and automatically adjust a split second before it ruins the part. We're also seeing green machining lubrication systems replacing massive floods of traditional coolant, which saves a ton of money and is way better for the environment. As multitasking machines blur the old lines of manufacturing, the done-in-one setup is the new normal. So whether it's breaking down your process steps, nailing down the quirks of your materials, or holding back on crazy strict tolerances, it all leads to one big question. On your very next design, how will you balance all this digital intelligence with the foundational logic of the materials? Hopefully today's explainer gave you some solid DFM principles to apply so you can create real commercial value in your supply chain. Thanks so much for joining us, and we'll see you next time.